Before I start this video, I want to make a quick correction because I realized I made a mistake. All these solutions down here are done using a different value for n. So solutions are for n equals 81. I think I had a prior version of this was n equals 64 and I didn't change it here. Anyways, all these are correct, or to show you the right way to do it if you're using n equals 81 instead of 64. For 64, a few things would change. The spread here would change. We'd get the spread would be 10 divided by the square root of 64, which is 10 over 8, which is 1.25. And that will have a minor change on our confidence interval as well. Instead of going from 15.82 to 20.18, it'll go from 15.55 approximately all the way up to 20.45. So now I'll start the video as normal and I'll go through. You'll see all the solutions to kind of see where these answers came from. But I just want you to note that the solutions will show n equals 81. Sorry about that mistake. Solutions for perfect problem 5 for Math 243. We're asked to create a confidence interval, specifically a 95% confidence interval for the average vertical of all NBA players. And to do so, I ask you to state the shape, center, and spread of this sampling distribution. We can do that. The shape ends up being approximately normal. And the reason it's approximately normal is because our value of n here, maybe I should have gone through and read the problem. The distribution of vertical leaps for NBA players is left skewed, or at least I'm claiming that it is. Most people jump really high, but there's a few that don't jump at all. With the standard deviation of 10, so this value of 10 right here is sigma. In a random sample of 64 players, so this is my value for n, the average vertical was 18, so I get x bar was 18. So the shape is approximately normal. Why is it approximately normal? Because my value for n is greater than or equal to 30. My value for n is 64. 64 is greater than or equal to 30. This is the central limit theorem here. The center, I don't know the center. I'm kind of trying to figure out the center. I'm trying to figure out mu. So maybe I'll write don't know mu, but so what we'll use is x bar to approximate it. So our center is x bar, our sample average, which is 18. And then the spread we want will be the standard deviation of our sampling distribution, which in this case is sigma divided by the square root of n. Maybe I should have written that first. Sigma over root n. And sigma in this problem is given as 10, and n is 81. So what we get is 10/9 here, something like that. And now that you got the shape, the center, and the spread, we can draw the picture. Sure, there's something that's let me try again. I don't know if that's any better, but it's going to have to be good enough. There's my approximately normal distribution. I don't know the center, so I'll use x bar to estimate it here at 18. And then what I want to do is figure out what values out here would make this area on the inside equal to 95%. I want to figure out how to make this 0.95 because we're making a 95% confidence interval. So there's a few different ways you could do this. We could do this using old methods and figure out these exact values, but your calculator also does it for you. If you hit stat here, and maybe I'll even write this, stat, well, if you go to tests, and then you go down to z interval, the 7th thing here, it'll make a confidence interval for you. We have data. Specifically, we know that sigma is 10. No, we don't have data. Sorry, we have statistics about the data. So we don't have the data itself. We have statistics about the data. I'll hit enter. We know that sigma is 10, that x bar is 18, that n is 81, and we want our confidence level to be 95%. And so if I go down here and hit calculate, what it tells me is that this point right here is 15.822. And that this point up here is 20.178. You could also use those, find those values using the inverse norm function, kind of the way we had been doing it. But since your calculator figures this out kind of a lot easier for you, might as well just leave it like this. I think this is a perfectly good picture, or you could say your confidence interval goes from 15.822 all the way up to 20.178. In other words, we don't know the average vertical for all NBA players. We don't know it. But what we do know is that in our sample, the average was 18 inches. And based on that information and what we know about the standard deviation, we can conclude that we're 95% sure that the true value for the population mean is somewhere between 15.8 and 20.178. These are low, 18 inches. Seems like NBA players could jump higher than that, but whatever, that's not the point. If this is true, this is our confidence interval. We're 95% sure that mu, the thing we don't know, is somewhere in here. All right, number two. Number two says, suppose I want a more exact confidence interval. I want the margin of error to only be 1 inch. So, okay, the way, kind of more formulaically, the way you can come up with your confidence interval is you take your point estimate, x bar, and you add and subtract what's called your margin of error. And the way you get your margin of error is it's a z value, z sub alpha over 2, times your standard deviation, which is sigma over root n. This right here is called your margin of error. Margin of error. So what it's saying in this problem is we want our margin of error to only be equal to 1. We want z sub alpha over 2 times sigma over the square root of n to be equal to 1. It says figure out what n would have to be. How many NBA players would you need to test if we want our margin of error to only be 1 inch, if we want this to be true? So if we can figure out what sigma and z sub alpha over 2 is, we can solve this equation for n. Z sub alpha over 2 is something we've seen before. It's what that's asking is what z-score would you need to only have 0.025 in this upper tail. So what I'm trying to say here is alpha, which is 1 minus our confidence level, is 0.05. So alpha divided by 2 is 0.025. And I can find z sub alpha over 2 by using the inverse norm function on my calculator, because the inverse norm function tells you what value has a certain area below it. So if I have 0.025 above this area, I can tell my calculator that I have 0.975 below this point. And since I want a z value, my mean will be 0 and my standard deviation will be 1. So inverse norm is a function that's under distributions, which is above variables here. If you go down to inverse norm, and you hit 0.975, comma 0, comma 1, it's going to tell me that z sub alpha over 2 is equal to 1.96 approximately. And now I have all the information I need. I know that let's try that again, 1.96 times sigma, which it told me was 10, divided by the square root of n has to be equal to 1. In other words, 19.6 divided by the square root of n has to be equal to 1. In other words, do I have any more room left? Oh yeah, plenty of room. Solve this thing for n. I could multiply both sides of the equation by the square root of n, and get 19.6 is equal to the square root of n. And then if I square both sides of the equation, I get n is 19.6 squared, which is what, just under 400? 19.6 squared. So that I get my value for n would have to be 384.16. Or you can't have 384.16 people, so I guess you'd need 385 players to make sure that our margin of error is at least that small. So if I wanted my margin of error to only be 1 inch, instead of looking at 81 players like I did, I'd have to look at 385 players. So this right here is my final answer, and that is the end of this problem.